We are in the flag end of concluding the syllabus. So without discussion of computational complexity theory, we cannot conclude the discussion of algorithms. Most of the time, I have heard from the many faculties that this topic will not be discussed because of intrinsic complexity which is there in this topic, and this is most confusing topic. Most of the time, people say like this. But without the discussion of this topic, we cannot conclude the discussion of algorithmics. So in the undergraduate level, we learn so many algorithms, and by using those algorithms, we learn different algorithm design techniques. But if we are very interested in this algorithmics, if we want to start our research in this, without having the knowledge of this computational complexity theory, we cannot start our research. So this is the topic of research. So research means if we want to start research, whether things can be done or not, that is very important. To know, we should know if we go in this direction, can we accomplish the task or not? That is very important. So without having that knowledge, we cannot go further. So this is the topic which gives the basic background of that. So in this video, we are going to discuss the basic concepts of computational complexity theory and non-deterministic algorithms, P, NP, different classes of problems, NP hard and NP complete class of algorithms. So before starting the topic, let us discuss some of the very famous quotes which may help us to understand this concept more clearly. So intellect distinguishes between the possible and impossible, and reason distinguishes between the sensible and senseless. Even the possible can be senseless. This was told by Max Born. So when we are doing something, when we are researching something, we think of doing something impossible, and we make it possible. Even if it is possible, sometimes it can be senseless. This should be there in the mind when we are doing something new. Say there is one more quote that is impossible only means that you haven't found the solution yet. Most of the researchers will start their research work having this in their mind. There is one more quote that is, if we fail to define carefully the rules of the game, our claims may end up in large dustbin of impossibility. That is, if the rules of the game are not defined carefully, then whatever we play in that game may become a dustbin or a mess. So with these quotes in the mind, we will start the discussion of computational complexity theory. In the preceding discussions, we had discussed so many algorithms. Definitely, algorithms are the best tools and most powerful tools for solving the problems, particularly when we are using modern computers on which we are going to execute them. But the power of algorithms is not unlimited. That should be in the mind. The limitations of the power of algorithm is the topic of this discussion. Say there are many problems which cannot be solved by algorithms. There are some problems which can be solved by algorithms, but not in polynomial time. There are some algorithms which can be solved by algorithms in polynomial time, but the lower bound efficiency is limited. So there are many reasons like that. So it is the thought in the computer scientists or computer professionals' mind when they are going to solve a problem, whether that problem can be solved in polynomial time or not. That will be the basic question they will be having in their mind. So we say that a problem can be solved in polynomial time if the worst case efficiency of that algorithm is in big O of P of n, where this P of n is a polynomial of algorithm's input size n. If so, then we say that algorithm can be solved in polynomial time. So if the algorithm can be solved in polynomial time, then we say that they are tractable problems. If that cannot be solved in polynomial time, then we say that they are intractable algorithms, intractable problems. Why there is this thin line of intractability has been drawn between the problems is because there are many reasons. Because if we represent the complexity in polynomial, then you can add the polynomials and you can compose a polynomial, and whatever addition and composition is there, that is also a polynomial. That may be one of the reasons. And the second reason is, say there are some problems like the complexity of the algorithm. So far we have discussed, say it may be, say, log n, n log n, say n square, n cube, say 2 raised to n factorial. Order of growth of different algorithms may fall in these categories. Say if you see all these categories, if there is a change in the input, the total time taken, if you change the size of the input, the total time taken by the algorithm, these algorithms is not so different. But if you change a very small size in the input for these kind of algorithms, say it is either Hamiltonian circuit or subset sum problem or tower of nine problem, if you change a very small size in the input, there is a very large change in the size of the output. This is what will happen. So these are all polynomial time algorithms. Say sometimes n raised to 100 is less than 2 raised to n. N raised to 100 is less than 2 raised to n for very large value of n. So if this is the case, there is no point in finding the algorithms which solves the algorithm with the efficiency of this. So we can draw this line. We can draw this line of tractability. We call these algorithms as polynomial algorithms, and the exponential algorithms which will take this amount of time as intractable problems. And the decision problems which can be solved in which are exponential, the definition of those algorithms can be converted to polynomial time. That is why we need to know what is tractability, what is tractable algorithm, tractable problem, and what is intractable problem. So if we can solve the problems in these, usually there are very less number of algorithms which are having the complexity n raised to 4, n raised to 5, and so on. Even though they are in this way, still they are polynomial time algorithms and they are decision problems. Say whether, say, for log n we are having a binary search, for n big O of n, say we are having a sequential search or linear search, n log n was got matrix multiplication n square. All the algorithms you take spanning trees or finding the path in the graph. So most of those are decision problems. Means they tell either yes or no. Either yes or no. So if there are that kind of problems, we say that is class P. That is class P set of decision problems that can be solved in polynomial time by deterministic algorithm. We have not yet discussed what is deterministic, what is not deterministic. We will go for that. Deterministic, simply it means that definitely it says something. Say if there is an instruction in the algorithm, it gives a proper output. Then it is deterministic, and it knows what will happen. So that is what we call it as deterministic. Does it mean that all the decision problems are tractable? No. The answer for this question is no. All the decision problems cannot be tractable. Okay, we'll see that when we go for NP. So this is the definition of class P. That is, if the problems can be solved in polynomial time by a deterministic algorithm, we say that they are the class P problems. So we have covered this part now. We will go to non-deterministic, then we will come back to NP. So every decision problem cannot be tractable. Okay, there are some problems which are not decidable, which are not decision problems itself. They are sometimes, even they are decidable, they are not tractable. So they are called decidable but intractable problems. There is a famous example by Alan Turing, who says halting problem. Tell about halting problem. There is a computer and an input. If that input is given to that computer, then that computer may go on computing the same continuously, or it may halt. Okay, so there are some such kind of problems. Say whatever we have discussed so long, like binary search, merge sort, insertion sort, okay, all the spanning tree algorithms, all those, they are decidable and actable, and they can be solved by a deterministic algorithm in polynomial time. But there are some problems which we have already discussed in the previous classes, like Hamiltonian circuit, traveling salesman problem, graph filtering problem, knapsack problem. All these are still, they are decision problems, but they cannot be solved in polynomial time. They take exponential time. What is common in all these problems? What is common in all these problems is it takes exponential amount of time or space as well for the output. And one more common feature in this is the complexity of solving these problems is very high, and once we get the solution, verification of that problem is not so difficult. Verifying that the output what we have got is right or wrong, checking this is very easy for all these problems. So verification stage is very simple. Say for example, if it is a Hamiltonian circuit, okay, only thing we need to say that we need to see that all n plus 1 vertices are visited or not only once. N number of vertices, one for returning into the back to the same vertex. And is there for every continuous consecutive pair of vertices, there is an edge or not? If we cross check these two, then verification of that problem is over. But developing the solution for Hamiltonian circuit for that instance of problem may not be so easy. So these are the common features in this problem. Because of these features in these kind of problems, computer scientists came for one more type of algorithms, that is non-deterministic algorithms. Even though after so much of research, they may not get the results. So they have to preserve their research work so that others can continue. Say all the algorithms what we have discussed, like merge sort, quick sort, all these algorithms, they were not known earlier. Once they started thinking in that they become non-deterministic algorithms, then they became deterministic algorithms. So this class of this P is expanding. That is, the problems solved in polynomial time are expanding as the research work is going on. So non-deterministic algorithm means it is a two-stage process. First stage is it is not known. Even the work is done, this process that stage is not known. It is non-deterministic stage or guessing stage. Okay, the second stage is deterministic stage, where people have found it that verification stage is easier. Say for example, in this non-deterministic search algorithm, assume that we are already having the best searching algorithm like the binary search, which will take log n to the base 2 of time. We want to reduce this to big O of 1. That is, only in one search we need to find the key in the given array of items. If this is the case, then we have to design. We are thinking to design an algorithm where there are some non-deterministic phases. Say for example, this choice, success, failure. These functions are not known. Just we assume that they will give the output. Okay, they are not defined properly. And we are also having deterministic part of this, that is verification part of this. if they non-deterministic phases give the result, then we know that we have done with it. Say there is an array from 1 to n, there are so many items, so we apply a choice function. We believe that it is going to give us the position of the key what we are searching, assuming that only in one search, one choice it is going to give us. Whatever it is going to give us, we are going to store that in j variable, temporary variable. If that a of j is equal to 0, if that a of j is equal to 0, then we print that j and we print success. We have found that key. If not, we are going to print 0 and failure. Here, all these three functions are non-deterministic. We don't know that it is going to give the position of correct key or not, but we believe that it is going to give us in the research stage. So this is the first stage of non-deterministic algorithm. Once it is known, then verification is very simple, and we know this process. That is what is our research. So if the problems are of this class, then we call them as NP class. That is, it is set of problems, decision problems that can be solved by non-deterministic polynomial algorithm. Non-deterministic polynomial algorithm. Then we say that is NP class. We say that NP class. So we came to know that every NP problem, every P problem was an NP problem once upon a day. So P class of problems are the subsets of NP. So non-deterministic algorithms will come from non-deterministic algorithms. So once upon a time they were non-deterministic, then they have become deterministic. So it is definitely P is a subset of NP. P is a subset of NP. But whether P is a proper subset of NP is still a question. Still it is under research. So definitely, if we consider P is some set of problems, then the larger set of problem is NP. Larger set of problem is NP, and P is a part of it. P is a part of it. It is going to increase day by day as the research is going on, and most of the problems which are decision problems which are solved, which can be solved by non-deterministic algorithm, if the non-deterministic phases in that non-deterministic algorithms becomes clear, they will be added to P. There is one more big research area, that whether P is equal to NP or P is not equal to NP. P is equal to NP and P is not equal to NP. So Mr. S. Cook, a great scientist, he affirmatively said that P is equal to NP. P is equal to NP. The proof of that is beyond the scope of our syllabus, but he says satisfiability is in P if and only if P is equal to NP. P is equal to NP. So when P will become equal to NP is this satisfiability constraint is satisfied. Okay. So to understand this satisfiability, we need to know one more term, that is reducibility. Reducibility. Reducibility means if L1 and L2 are two problems, if L1 can be solved in polynomial time deterministic algorithm, then L2 can be solved in the polynomial deterministic algorithm. That is, we write like this: L1 is reducible to L2. L1 is reducible to L2. With understanding of this, we can go for discussion of NP hard and NP complete problems, NP complete classes. So every problems which are NP, if they can be reduced to a decision problem of polynomial time deterministic by a deterministic algorithm, then they can be put into the category of NP hard. NP hard. Non-deterministic algorithms which were there in NP, if we are able to transform them or reduce them to a problem of deterministic polynomial time, then we say that it is NP hard. We say that reducible to it. Reducible to it means still we don't know they can be solved. There are large classes of problems which are not yet solved in polynomial time. If we are able to reduce them to it, then we say that they are NP hard problems. If a problem is NP hard as well as it is NP, then it is called NP complete. Then it is called NP complete. So as the research is going on, this circle may expand. This circle may go on expanding, and one or the other day it will reach to this one. Say Hamiltonian circuit, traveling salesman problem, knapsack problem. They were unsolved problem once upon a day. Unsolved problem once upon a day. But now we are able to solve them, but not by a deterministic algorithm. For every instance will take this amount of time. We cannot say like this. Okay, different instances will take different amount of time, and also as there is a small change in the input size, the exponential, it is taking exponential amount of time. But even though they are hard, we can solve it. If we are able to find a deterministic polynomial algorithm, then this circle is going to expand. This circle is going to expand. So this is a very interesting area of research. One can think of doing this. One can think of doing this. So NP hard means a problem L is in NP hard if and only if the satisfiability reduces to L. Or it means that a problem is NP hard if every problem in NP can be polynomially reduced to it. Every problem in NP can be polynomially reduced to it. This large class of NP can be if we are able to polynomially reduce to it, then we can say that is NP hard problem. Say for example, all the optimization problems like earlier what we had discussed, Hamiltonian, knapsack, traveling salesman, all these you can put them in this category, that is NP hard. And if we are able to polynomially convert them to a problem, then decision problem, then we can say that they can be solved in NP complete class. They can be solved in NP complete class. Say for example, L1 is a decision problem, L2 is a optimization problem. Then L1, if we are able to convert L1 to L2, say for example, knapsack problem is an optimization problem. Definitely we can convert it to a decision problem. Say graph coloring problem is an optimization problem. If we convert it to M coloring problem, then it is a decision problem. If we are able to convert like that, then it is NP hard problem. We say that a small set of problems which can be converted like this, they are in NP and they are also in NP hard. They are the subset of NP. So the subset of NP hard, then we say that they are NP complete class. They are NP complete class. So the best example is knapsack problem, which can be considered as NP complete, and it is also NP hard, and it is also NP. It is also NP problem. So very interesting topic is as we are able to decrease the non-deterministic feature in those problems, they will be added to the P class of problems. Thank you.